Module 9? Interesting, I said Chapter 9 here. I meant Module 9, it's actually Chapter 10, I believe, in your textbook. So this is hypothesis testing where we involve two samples. And sometimes those two samples are from two different groups. And sometimes we have two samples taken at different times, perhaps to compare the effect of a treatment, for instance, among the same individuals. In both cases, we'll have two separate samples, but in those two situations, we'll actually end up running different tests. It turns out in the first case, with two completely separate groups, we have to run a test for the difference between the two groups. And so that's going to be one of these two sample tests that we'll talk about. One of the drawbacks of that is the formula for instance, degrees of freedom is exceptionally complicated here. I strongly encourage using a calculator to compute everything for this module. In the second case, however, if you are taking two samples at different times, for instance, among the same individuals, that's called a paired sample. And in that situation, you can actually compute the difference among the pairs, and it ends up being a single sample once you've done that. So you just treat it as if it's a single sample among those differences. And I'll recap that when we get to that portion here today and do another example near the end. Okay. So I first want to talk a little bit about what's different as far as testing with two hypotheses. It's mostly going to be a recap of what I just said a moment ago, but there are also some different conditions to check. And then we'll talk about how to compute hypothesis tests in each of the three cases that we need to know. We'll talk about hypothesis testing for two proportions and hypothesis testing for two means. And it's different in the situation that you know the population standard deviation versus the situation that you know the sample standard deviation. But as always in practice, we almost never know the population standard deviation, especially for two separate groups. So in most cases, when we compare two means, we're going to have to use a two-sample t-test. The last portion is just a brief one showing you how to handle the paired sample situation, and it ends up falling back on what we just saw last week. Remind me at the end, I do want to remind everyone about this as well, but while I'm thinking about it, this is the last module in our third unit, which covers modules 7, 8, and 9, and so we will have an exam covering those three at the end of this week. I think it will open, I guess, I've had them opening on Fridays and going through Sunday, so it will open a week from tomorrow. Okay. All right. So let's think about how our hypotheses might be different here. If we are collecting two different samples to try to compare two groups, generally the comparison we're trying to make is to know whether they have a different average or a different proportion. And this is where it helps a little bit to think about what it means to be different. If they're the same, then when I subtract the values, I will get 0. That's one thing that, if P1 is equal to P2, for instance, then P1 minus P2 is 0. But if P1 is not equal to P2, then P1 minus P2 is not equal to 0. And that's really what it means to be different. It's just that when I subtract them, I don't get 0. So that's actually how we will set up our hypotheses here. Our null hypothesis will be that the difference between the two groups' values is equal to 0. And then our alternative will either be that they are not equal to 0, or that they're greater than 0, or that they're less than 0. Depending upon the situation, which one are we trying to prove? And especially with those questions in MyOpenMath, I would strongly encourage you to think about if I can reject the null hypothesis, what would I like to conclude? Is the question asking me to show that one is larger than the other, or is it just asking me to show that they're different? If it's wanting me to show that one is larger than the other, then that's where I'll need to use a one-tailed test, either a greater than or a less than, depending on which one I want to be larger. And then if it just wants to know if they're different, then I will use not equals. So this is summarizing that. Most of the time, your null hypotheses, in the case of proportions, will look like this one. P1 minus P2 is equal to 0. And your alternative will either be that it's not equal to 0, or that it's greater than 0, or that it's less than 0. And again, just pay attention to the context of the question to know which one of those is correct. When we compare two means, we want to know whether the mean from group 1 and the mean from group 2 are the same. And again, just the same idea. If mu1 equals mu2, that means that mu1 minus mu2 equals 0. And if they're not equal, then their difference is not equal to 0. So our null hypothesis there will almost always be that the difference is equal to 0. And our alternative will be either that it's not equal to 0, or that it's greater than 0, or that it's less than 0, depending upon whether we want mu1 to be bigger than mu2, or mu2 to be bigger than mu1. Right. Which one of those would we like to conclude if we're able to reject the null? Alright, so that's the idea. You will notice that there is the possibility of pooling versus not pooling variances. And for now, I'm going to simply say that the value of pooling variances, first of all, you can only do that when you know that the variances are the same among the groups. Okay? Now, in most situations, that's actually not going to be something you know. You have to have strong reason to believe that your first group and your second group have exactly the same variance. And if you're trying to understand whether they have a different average, then the chances of you knowing that they have the same variance are very, very small. So that's the first situation there. It makes it unlikely that we'll be able to pool. If you are able to pool, it does, in some situations, increase the power of your test. But in this particular situation, with just 2 samples, it doesn't really do much. It doesn't provide much of an advantage at all. So in practice, in this course, we are not going to be pooling variances for any of these calculations with 2 samples. It does actually hold value when you have a larger collection of samples. So if you're comparing multiple groups, and there are situations in the chi-squared tests where you might want to pool variances. We'll be talking about chi-squared in the last unit, but not in this unit. In this unit, we do not pool variances at all, so we will only use unpooled. And when you use Bogdan's calculator, make sure that you are not pooling the variances. All right. So there's another thing that's really important to think about when you're talking about 2 samples. Are my samples matched pairs, or are they independent? Okay, and that's the difference I was talking about before. Am I looking at a before and after among the same individual? In that case, they are paired. Or am I looking at 2 completely separate groups? One thing that makes pretty clear that you're looking at separate groups, at least in most situations, is if you have a different number in the 2 samples. Right? I can't have multiple samples from every individual if I have 15 samples in my first group and 25 in my second group. Right? That's clearly not going to be paired, at least not completely. But things to look for to know, am I looking at a matched pair situation or independent samples? Check whether you're drawing multiple times from the same individual. If so, it is definitely matched pairs. That will be treated differently than what we do in these first 2 units. Are the differences calculated from the matched or paired samples? Again, if so, unfortunately my footnote is lost here. We'll talk about how to do that later. The differences in that situation would actually form the sample that we use for the hypothesis test. And we also have to have the matched pairs having differences that come from a population that is normal or that has a sufficiently large number of differences included in the sample that we can then conclude that the sampling distribution is approximately normal. And so we would need at least 30 matched pair differences for that to take effect. Or if we know that the pairs themselves come from a normal distribution, then that's okay as well. In that situation, if any of those things are true, usually it's multiple things, then you're looking at a matched pairs test. And like I said before, that is not going to be treated as a 2-sample t-test. Instead, that's going to be a single sample that we compute by taking the difference among the matched pairs themselves, with the sample size being the number of pairs that we include. Okay. All right. So we will get to that in a few minutes. Let's start first by thinking about how can we do a hypothesis test for 2 samples where we're looking at proportions. That is, if I want to know whether 2 groups have distinct proportion values, I don't know anything necessarily up front. All I have are samples from each group. Okay. Well, in order to run the hypothesis test the way we're going to construct it, I need to check 3 conditions, and they're going to look very familiar. The first and the third one are exactly the same as what we needed for proportions in general. But the second one here is a little different. Let's recap all of these first. The independence assumption needs to be true within each group. So if I'm comparing group 1 and group 2, what I need is that all of the members of my sample from group 1 are independent of each other. I also need that all of the members from my sample in group 2 are independent from each other. That's the independence assumption in each group. As usual, that is difficult to establish directly, but the most likely way we do it is we make sure that our samples from each group were collected with sufficient randomization. And if that's the case, then the randomization condition gives me independence within the groups. Now, because I'm comparing two different samples here, I actually have an extra condition to check for independence. What I need is that the two groups are independent of each other. In most cases, if you're actually testing two different groups, it should be relatively obvious that they're independent from each other. But it is a question you need to ask. You do need to verify that. If they are not independent, then you don't have the independence of your samples, and that leads to a breakdown of the distribution we're trying to use to compute the hypothesis test. And then lastly, we do need to check the success and failure condition. Because we have two different samples, we need it to be satisfied within each sample. So whatever I'm calling a success or a failure in terms of my proportions, I need my sample from group 1 to include at least 10 successes or 10 failures, or if I'm doing this beforehand using a null hypothesis, I need to expect at least 10 successes and 10 failures in the group. And the same thing is true for the second group. I need to observe or expect at least 10 successes and at least 10 failures in that group. If all three of these conditions are satisfied, then I can use my standard hypothesis test for two samples comparing proportions. All right. So what does the distribution look like? If those conditions are satisfied among my two groups, then my difference of proportions as a sample will have a normal distribution. That's great, that's familiar. And the center of that normal distribution will be the true difference between the proportions among the groups. If P1 and P2 are the true values, then P1 minus P2 is the true difference, and my sample observed difference will be normally distributed around that true value. So the center will be at the correct value. And the standard deviation of that sampling distribution, or the standard error, is computable here as well. Unfortunately, it's not quite the same as what it was for one sample. It's not terribly different. If you remember, when we had one sample, we had the square root of p times q over n. What we have here is the square root of p q over n plus p q over n, where we're doing it for each group separately. And the reason this works, actually, it's often been called the Pythagorean theorem for statistics. There's an interesting property that variances among two random variables simply add. If I want to find the variance, let me actually do this on the document cam here. If x and y are independent random variables, then the expected value of x plus y does exactly what you would want. It's the expected value of x plus the expected value of y. So if I have two different things I'm adding together and I want to know what happens to their averages, well, their averages also add. That's a linear property. It's actually really, really nice. Works the same way with differences. Alright, if I take the difference between x and y, the average for that difference is going to be the difference of the averages. It takes a little checking to see this, but it's not that hard to see, and that is actually the correct value, which is kind of nice again. Variance, on the other hand, is a little weird. Long story short, the variance of a sum of two independent random variables is the sum of the variances And the variance of a difference is also the sum of the variances. So it doesn't matter whether I add or subtract here. When I'm combining two random variables, I end up getting this result. In fact, there's an interesting way to look at this. If I take any multiple of the first variable plus any other multiple of the second variable, and these could be positives or negatives, so I could be adding or subtracting these. What happens is, because the variance ends up being a squared property here, I get a squared times the variance of x plus b squared times the variance of y. And so when I'm trying to find the equivalent property for the standard deviation, remember the standard deviation is the square root of the variance. And so you get this kind of square root of a squared plus b squared idea. This is where the idea from the Pythagorean theorem comes in. Okay. Long story short, if I'm looking at the variance among two different proportion samples, the variance for P1 is P1Q1 over N1, and the variance for P2 is P2Q2 over N2, so that the standard error is the square root of those two things. Remember, that's what we used in our one sample distribution. So if I'm looking at the difference between P1 and P2, I'm simply going to add these variances and take the square root of that sum as the standard deviation. So if we jump back over to the computer at this point, that's precisely the formula given right here for the standard error. It's simply the square root of the variance for the first sample plus the variance for the second sample. I'm not terribly concerned about whether you remember the ideas that I just mentioned there about how variance is additive, whether you add or subtract the variables, but that's where it comes from, and that's why this looks almost like what we saw before, where we're just adding them together. It's because what we're looking at is this is the variance for the first sample, and this is the variance for the second sample. So when I add them together, I get the variance for the combined sample, for the difference of the samples. And then the square root of that will be the standard deviation, or the standard error. Alright, so this gives me a normal distribution. Once I have that, I can take my observed difference, I can compare it to what that distribution would imply if I have a null hypothesized difference. And then from that, I can compute a test statistic and a p-value and decide whether or not to reject my null hypothesis. I either reject or I fail to reject. Remember, we never accept the null hypothesis. Okay. So this is just outlining that basic set of steps. The first thing to do is to either check the conditions or formulate the null hypothesis. I really don't care which one of those three things you do first, but they should be the first two things in either order. The null hypothesis I will want to use pretty much every time here is that the difference between the proportions is equal to 0. And then my alternative will be either that it's not equal to 0, if I don't care which side it comes on, I'm just asking if it's different, or that it's greater than 0 or less than 0, depending upon whether I want to show that P1 is bigger than P2, or that P2 is bigger than P1. If I want to show one of those two things, it needs to be a one-tailed test. Make sure to check those three conditions. There's two of them for independence, and then there's the third one that is for successes or failures in both groups. Okay. After that, I can compute a z statistic. From that, I get a p-value using this z on the standard normal distribution, and I compare that p-value to alpha. If it falls under alpha, I'm allowed to reject the null hypothesis and conclude instead my alternative. If it does not fall under alpha, then I have insufficient evidence to reject the null hypothesis. So I fail to reject, and there's no other conclusion I can draw. Okay. So I think the easiest thing to do here is to actually do a couple of examples. So let's start with this first one. Suppose that we have an advocacy organization that wants to know whether the proportions of individuals who are born outside the country are the same for Americans versus for Canadians. And so this organization surveys 1,000 Canadians and finds 192 of them report being born in another country. They also surveyed 1,200 U.S. citizens and find 188 of them were foreign-born. So that they're testing whether these two things are different. This is a two-sample test. Okay. So what we need to do first is formulate our hypotheses, and then check those three conditions, and then we can compute the test result. So what I will do is I will write down on paper those first three steps, and then we'll jump over to the Toboggan calculator to see what the test itself looks like. All right. So let's start with what are my two groups here. Let's call group 1 the Canadians, and group 2 the Americans. Okay. All right. So how many did I sample from group 1? Sampled 1,000. And my success rate was 192 out of 1,000. And so then my failure rate was, let's see, 808. Yeah. For the Americans, I surveyed 1,200 of them. I don't know what that is, so let me do my calculator here real quick. 188 out of 1,200. .1567. It's actually 0.156 repeating. And then my Q value from that, oops, I called that a 1, I should get 2 here. My Q value from that is 0.8433. And with that 3, continues on indefinitely. Okay. What is my null hypothesis? I want to test whether these two have the same proportion. And so if they do, then the difference between the proportions is the same. All right, I should be clear. This is the observed values here. So my null hypothesized value is that P1 minus P2 equals 0. That even though I saw a difference in these two samples, that if I compare them as populations, I'd find that there's no difference. What alternative do I want to conclude here? Let's check the exact phrasing. They want to test if they are the same. So they're not saying that one is larger than the other, and that means that all I want to conclude is that either they are, well, I want to test if they're the same, and if I can, I will conclude that they are not. That's all I can conclude here. All right. So if the three conditions I need are satisfied, then the distribution I will get is that my observed difference of proportions will be normal with, well, under my null hypothesis, a center at 0, and then a standard error given by the P1, Q1 over N1 plus P2, Q2 over N2, all under the radical. Don't have room to write that here. Let me just do it this way. Okay. All right. So let's check those three conditions. First condition, I need independence within each group. So, they surveyed 1,000 Canadians. I guess the question does not indicate whether that is a random sample or not. Let's presume that it is. If it's a random sample, then that group, I will assume, is independent. That means within the group, the respondents who contributed to P1 and to Q1 here are independent of each other. Okay. All right. Same thing for the second group. If this survey was conducted with enough randomization, then I will assume that each of the 1,200 members of this group are independent of each other. and that gives me the independence assumption. Again, I'm getting it from randomization. All right, what's the second condition to check? The independence between groups. Would I expect one of the Canadians' responses to have an influence or a connection to one of the Americans' responses? Probably not. The chances of those two things having an impact on one another, knowing the response that one gives, should not help me in any way determine the response that the other gives. As long as that is true across the two groups, then the two groups themselves are independent, so that's the independent groups assumption. And the last condition to check is the successes or failures condition. I need at least 10 successes and at least 10 failures in each group. Well, I have 192 in group 1 and 188 in group 2, and I guess 808 and what would it be, 1,012. So each of those four numbers are bigger than 10, well bigger than 10 in fact. So this satisfies the successes and failures condition. That tells me that I can run my test. So what I'm going to do is I am going to jump over to Bogner's calculator yet again. And here I'm doing a two-sample test. I'm testing for a difference between proportions. So you'll notice under his statistical inference there's a related one for the difference between proportions. All I need to do is to input the samples themselves. I have 1,000 in my first group with a success rate of 0.192. In my second group I had 1,200. And in fact, I can be more specific here. There were 188 successes out of the 1,200. I don't need to put in the rounded value. So it will compute this for me. And you'll see, sure enough, here's my formula for the standard error. The square root of P1 Q1 over N1 plus P2 Q2 over N2. What am I testing for? I'm testing for a difference of 0. I simply want to test, is it not equal to 0? Do not check this box in this instance. So what I'm looking for then is a test statistic of 2.17. What p-value do I get from that? 0.03. Okay. So 0.03 as a test statistic, as a p-value, falls under alpha. So it's right here inside the rejection region. That means I can reject the null hypothesis here. I can conclude that these two groups are actually different. In other words, there was sufficient evidence to conclude that the proportion of Canadians who are foreign-born and the proportion of Americans who are foreign-born are different. Now, just to show you what would happen if I were to use pooled standard error, what that does is it combines the variance calculations, and you'll notice the result is a larger test statistic and a smaller p-value. So it does give you a little bit more power. It does make it more likely that you'll be able to reject the null hypothesis. But as I said, in this class, we are generally not going to use pooled standard error for these types of questions. So that's what I would expect. A p-value of 0.03 gives me enough evidence to reject the null hypothesis. Okay, questions about that example? Well, let's do one more. Suppose a consumer magazine polls car owners and wants to see if they're happy enough with their vehicles that they'll purchase the same model again. So they randomly select 500 owners of American-made cars and 500 owners of Japanese models. And suppose they find that 72% of the owners of American-made cars and 74% of the owners of Japanese-made cars say that they will. Is this evidence of a difference between the two groups? So, in order to do this, we have two separate groups. We're trying to test whether they are different. This is a hypothesis test for two proportions, for the difference between two proportions. And so what we'll do is our null hypothesis will be that the difference is 0. That is, that the two groups have an equal likelihood or equal express preference for buying the same model again. And we'll compare the difference that we see here, the 72% among this 500 and the 74% among this 500, to see whether that's enough to conclude that in fact they actually are different. Before we can run any of those tests, we have to check those three conditions. Would we expect independence within each group? So first of all, within the American-made cars group, we have a random selection of 500, so that randomization should give us independence within the American group. Similarly, within the Japanese group, we have a randomly selected group of 500 owners, so that randomization should also give us independence. So that gives us the independence assumption within each group. Can I assume here that the two groups are independent of each other? Would I expect, knowing whether one individual in the American-made group will or will not buy the same model again, to have any impact on my assessment of whether a corresponding person in the Japanese group will or will not buy the same model again? I see no reason whatsoever that they would be connected. Okay. So those, I think, are independent. That gives me the independence of the two groups. And lastly, I need the success or failure condition. I have 72% of the 500, and I guess then 28% of the 500. Both of those are easily more than 10. And 74% of 500 and 26% of 500, again, are easily more than 10. And would be 0.2%. So I'm well beyond that. All right, so that gives me all three conditions I need. That means I can use the normal distribution for my sampling distribution, and from there I can run my hypothesis test as normal. So I'm going to do this by jumping straight over to Bogner's calculator. We'll just input the data. So clear all this out. Okay, so I had 500 in each group, and in the American-made group I think it was 72%, and in the Japanese-made group it was 74%. So we want to test, are the differences here 0? And let's double check. All it asks for is there a difference? So not equal to is my alternative. The critical value I want to test against to get 5% of the area in the two tails would be 1.96. What's my actual z-score? Negative 0.712. That means in my group I saw that the second group seemed to have a higher percentage or higher proportion. But that is not outside of this region. It's not in the tails. It's right here, which is well within the 1.96 reasonability range. So my p-value reflects that. I get a p-value here of 0.476. That is way more than alpha, which I used 0.05. So that is not enough evidence to conclude that the groups are different. I fail to reject the null hypothesis, and I have no actual conclusion from this. Maybe they're the same, maybe they're different. I would need a lot more information. Perhaps a much bigger sample to conclude that they are different. To emphasize that, suppose that these were actually the true values. In order to get enough evidence to reject the null hypothesis, I would need to have a lot of sample members to show that that difference of 2% actually matters. If I had 5,000 in each sample and I still found 72% and 74%, well, in that case, I do have enough evidence to reject the null hypothesis, because the difference of 2% among a much larger group is more significant. I have more evidence at that point that they are actually different. Okay? But in my example, I only had 500. So in that situation, I did not have enough evidence. My p-value was well beyond the threshold for rejection, so I failed to reject the null hypothesis. Okay? I'm starting to lose my voice here. So it seems like that's a good point, or a good place to take our first break. Are there any questions about hypothesis testing comparing two proportions? All right. Well, let's take a 5-minute break. On my clock, it is 9. Well, 9:58. So let's return at 10:03, and if you have any questions, feel free to ask them at that point. I'll see you at 5. Hypothesis test. Even though the ideas are not terribly different than what we've seen before, once you understand how variances add in the same way, there's obviously still a lot of calculations to be done there, so I would strongly encourage you to use your calculator to compute this. If you have a handheld calculator, one of the TIs for instance, they will compute a z-test for two proportions, a two-sample z-test. Your book walks you through that process, and I can also help you out with that if you need during my office hours or via email. If you do not, which is the case for most of us, then you can use Bognar's calculators to compute this. So that's what I would strongly encourage you to do. Okay, so are we ready to then look at a difference between means? Ready or not, here we are. All right, so if I'm comparing the mean between two groups, that is, I want to compare whether the mean from group 1 and the mean from group 2 are the same or are different, or perhaps I want to know whether one is greater or one is less than the other. The first thing I'll need to do is to check 3 conditions, and all 3 of these should look familiar at this point. The first one, this has been true of every test we've run so far. I need to check the independence assumption within each group. If I collect samples to average from group 1 and samples to average from group 2, I need that all of the members of group 1 are independent of each other, at least the values that I'm measuring for those members. And the same thing is true for this second group. I need all of the members included in my second sample to be independent of each other. That's the independence assumption. As always, very hard to prove directly. We usually get it by assuming randomization of our sample. We also need the independent groups assumption. This is the same idea that we saw in the previous example. What that means is when I'm taking the average from my sample from group 1 and the average from my sample from group 2, I need to know that the values for each of the members of those samples are independent of each other. So I need to make sure that there's not one common thing that might be influencing the values of those members of group 1 and those members of group 2 to be connected. As long as that's true, then I have the independent groups assumption. Again, very hard to establish directly. Usually you just need to convince yourself that there's no reason why they would be connected. It is an important consideration, however, because if you can see a reason why the members you surveyed or included in your sample in group 1 their average might help you to find the average in group 2, then in that case you don't necessarily have the independent groups, and that breaks this distribution down. The last condition we need is we need the nearly normal condition, because we're looking at means here. We want the individual groups themselves to have a roughly normal distribution. That is, when you look at a histogram for this group, do you see something that appears to be essentially unimodal and symmetric? Again, it doesn't have to be perfect, but if it's close, then we can use the distribution we'd like to see. And I forgot to emphasize, in the independent groups assumption, if we have a paired sample, if we're measuring something from one individual before and after a treatment, if it's the same individual, then obviously those two things are going to be connected to each other. So those two groups of measurements would not be independent. And that's one of the many reasons why we cannot use a two-sample test in that situation. We don't have independence of groups. Those are paired samples, so what we end up doing is we construct a single group from those paired samples, and then if each individual is independent, then we're okay. And that's really what we aim for. We'll see that again at the end of the discussion. All right, so check these three conditions. If those three hold, then we do have a distribution we'd like to use. Now, if we happen to know the population variances, remember what happened in a single sample case, we can compute a confidence interval with the standard error built by by the average. The standard error was the sample variance, the population variance divided by the square root of the sample size, sigma over the square root of n. Okay. And now the standard error for this sampling distribution of differences works very much the same way as what we saw for proportions. If those conditions check, then the distribution I would get is a normal distribution. Its center is the true difference between the means, and its standard error, that is the measurement of its standard deviation as a sampling distribution, looks like this, which you may recognize. The variance of the first sample as a single sample is sigma squared over n. The second one is sigma squared over n for each of the two sigmas. And so since variances add, when I add those, I get the variance of the sampling distribution, so the square root of it will be the standard deviation. That's an explanation for where this formula comes from, but it's the same idea. I'm essentially taking the square root of the sum of the two variances because I'm subtracting two separate groups, and the variances always add in that situation. Okay. So that's great, and that gives us a relatively clean formula with a normal distribution, which we know how to use. Now, I'm going to dispense with the obvious here, because how likely is it that I know sigma 1 and that I know sigma 2? If I understand the groups well enough to know their standard deviations, their actual standard deviations as a population, then I probably don't even need to ask this question. I would know enough about their means to know whether they're different or not. Right? There are situations where I might have an estimate and I feel confident that estimate is correct. In that situation, I could use this, but that is so rare and so unlikely to be useful in practice that I'm just going to step aside from that. Most of the time, we don't know either one of these things. Instead, we have to use our sample standard deviation from group 1, our S1, and our sample standard deviation from group 2, S2. And as we saw before, when we have to use a sample standard deviation in place of the population standard deviation, we no longer get a normal distribution. What kind of distribution do we get? Anyone remember? Module 8, when we did a single sample, and we tried to build, for instance, a confidence interval or a hypothesis test for means, when we had to use this sample standard deviation, we were forced to use a t-distribution, right, as an approximation to the normal distribution, because we're using our sample standard deviation, not our population one. In practice, that's usually what happens, because we usually don't have access to the population standard deviation. Now, with a t-distribution, if you'll recall, each distribution is different for a different number of degrees of freedom. So I need to figure out how to calculate the degrees of freedom between my two groups. So hold that thought. In practice, this is exactly what ends up happening. Because I have to use S1 and S2 instead of sigma 1 and sigma 2, I don't have the population values, so I have to use the sample values as a stand-in. I'm forced to use a t-distribution with a number of degrees of freedom, which I'll talk about in a moment. That t-distribution will be centered around the true value, which is good, and it has a standard error that's pretty much exactly what I'd expect, where I've simply replaced my sigma 1 with S1 and my sigma 2 with S2. So both of those things are very nice. They're pretty much the best I could expect to happen. As I said, I have to have a number of degrees of freedom, and unfortunately here, my degrees of freedom, they don't just add. There's some complicated things happening behind the scenes. Long story short, this is the formula that gives you the number of degrees of freedom. Okay, I use nu because that's usually the symbol that, for instance, Bognar's calculator will use. And what you would do is you would take, the square here, the variance, and square that, and then you take 1 over n1 minus 1 times the square of its variance, and 1 over n2 minus 1 times the square of its variance, and add those together in the denominator. So it's kind of like a ratio of squared variances. It's complicated. Obviously, there's lots of places to make a mistake here, and in practice, this S1 and this S2 are almost never nice numbers. As we've seen before, when we calculate a sample standard deviation, we usually get a decimal expansion. And Bognar's calculator gives us 4 or 5 decimal places. Excel can give you more. Long story short, this is not going to be a nice number, and if you do any kind of rounding at all, you're going to have error that explodes here. I do want you to use a calculator to compute this. Do not try to compute this by hand. It can be done. It's not that it's impossible, but it's very difficult to do it correctly without making mistakes somewhere. And another thing to realize, in our previous cases, the degrees of freedom was always an integer. And one advantage of that is if you are the type of person who prefers to use a table of values, you actually can look up in a table of values to find a t value, a critical t value, for the correct number of degrees of freedom, if the degrees of freedom are an integer. If they're not, then you kind of have to round, and that's going to lead to some error there as well. But with a calculator, we can use the exact number of degrees of freedom, which gives us the most accurate result we can. It gives us the strongest power for our test. All right. So let's see if we can actually do this in practice. Okay. Here's how we'll do the test. Very similar to what we did before. We start by setting up our null hypothesis. If we're testing for a difference between two means, we test with the null hypothesis being that there is no difference. That is, my null is that mu1 minus mu2 equals 0. Depending on what I want to conclude, if I can disprove that, I will formulate an alternative that is either mu1 minus mu2 is not 0, mu1 minus mu2 is bigger than 0, if I want to show that the first group is bigger, or mu1 minus mu2 is less than 0, if I want to show that the second group is bigger on average. Then I need to check those three conditions. Okay. Remember, independence within the groups, independence between the groups, and the nearly normal condition. If those three conditions are satisfied, then I can use the t-distribution that I want to use. I will compute a test statistic t. Do not do this by hand. Again, it can be done. It's not impossible for calculators. That's how we did this. But it would be exceptionally difficult to do it correctly because of all the different pieces that are involved here. And definitely, among all things, let your calculator compute the degrees of freedom. You do not want to compute this formula and get a decimal approximation that's wrong in the third decimal place and miss everything because of that. instead use the calculator to compute the degrees of freedom. It will then give you a p-value using the distribution that you need, and you can compare that p-value to your level of significance to decide whether to reject the null hypothesis or simply fail to reject it. All right. So questions about the basic idea? Okay. And let's do a couple of examples. I went backwards. That was interesting. There we go. All right. So in Olympic running events, the preliminary heats, those that lead up to the final, are determined by a random draw. And so we'd expect that the ability level of the runners in the various heats to be about the same on average. It should be the case that they're relatively equally distributed, so there should be no reason for one heat to be significantly different than another. This table gives the times in seconds for the 400 meters women's run in the 2012 Olympics in London for the two preliminary heats, the second one and the fifth one among the group. I forget how many there were. I think there were like about 10 or so. Is there any evidence that the mean time to finish is different for the randomized heats? Now I'm ignoring two individuals here. There was one who did not finish in Heat 2 and one who did not start in Heat 5. So I'm just throwing those out and pretending like they weren't part of the group. And that left 5 runners in each heat. So how would I do this? Well, first I need to set up my hypotheses and check the associated conditions. So my hypotheses would be that the difference between the average time in Heat 2 among those runners and the average time in Heat 5 is 0. Okay. Now obviously in this particular example, for this particular run, I'm going to get a difference that's not 0. The question is that difference enough for me to conclude that these two groups of runners are not the same on average? That is, were they different enough this one time to conclude that they're actually different as runners? Looks like, hard to say. Looks like in most cases the first group ran a faster run, although our outlier here is significantly worse than anyone in the second heat. So it's hard to say for sure. But I think the average here is going to come out a little lower than the average here. And so the question is it true that the runners in Heat 2 are better on average than the runners in Heat 5? Or is it just that I happen to see a slightly different group this one time? Is it a luck of the draw process of sampling variation? All right, so those are the things I want to test. My null hypothesis is that the difference is 0. And since I just want to know if the mean time is difference, I'm not trying to conclude that one is bigger than the other. I will do a two-tailed test. So my alternative is just that they are not equal to 0. We'll do that in Bogdan's calculator again in just a moment. Probably I'm going to have to calculate these values, and I'll use Excel to do that. Okay. All right. Let's check the 3 conditions. First condition, independence assumption. Are the values in each of these 5 independent of each other? What do you think? It's a natural question. Would I think that this runner's average, this runner's value, and this runner's value would be connected? I could see arguments in both directions. They're completely separate runners, and they're both trying to do their best, so I would assume that they're probably not connected using that reasoning. But I could also see, if you've watched races, sometimes one runner can push the field to run harder, especially in a preliminary heat, where you're not necessarily eliminated if you do poorly, but it can change your chances or what lane you get to run in later runs. And so if the group is doing better, you might actually push yourself harder, versus if the group is not doing better, you might actually hold back a little bit and say, well, I'm going to take it a little easy here and reserve my energy for the later runs. I could see a situation where you could say that those things would be not independent. But let's assume, for the sake of argument, and because I want to actually run the test, let's presume that they are independent. Is there an independence between the groups? Would I expect the average in group 2 to have some, or the values in group 2 to have some impact on the values in group 5? That is, knowing that this runner averaged or ran a 51.05 second 400 meter run, would that help me understand what this runner did in heat 5? Would it make it more or less likely that they ran a certain value, or within a certain range of a certain value? Not that I can think of. I can't see any reason why knowing a value from this group would help me in any way to know a value from this group. Okay. Other than the fact that they are all Olympic quality runners in the same event, so they're likely to be relatively close together. Other than that, I see no information I'm going to gain from one of these individuals that would help me with understanding one of these individuals. Okay. And if the two groups were distributed with enough randomization, then it's probably true that the groups themselves are independent of each other. Okay. All right, so that gives me the first two conditions. The last one I need is the nearly normal condition. And I don't have enough information here to conclude anything, but let's just assume that the run times for runners who are of Olympic quality are roughly normally distributed. That is, if I were to look at the different times that they ran under a large number of races, that I would expect to find that that histogram is unimodal and roughly symmetric. If that's true, then I can use my hypothesis test for means with the t-distribution. I do not have access to the average across the population of Olympic runners, nor do I have access to the population standard deviation. So I'm going to have to use the t-distribution, and what I will do is I will compute the sample standard deviation for this first group and the sample standard deviation for the second group. All right. Well, let's see what we can do here. Ink. Yes, I can highlight this. That's helpful. Let's jump over to Excel. There's Excel. And I will just paste. All right. Bear with me while I make them separate values. Alright. So this is heat 2, I think it was. Make sure. Yep. And for heat 5. Copy those values down. Okay, good. Sorry, just cutting and pasting all but the one I want to keep there. All right. Sample averages and sample standard deviations. Notice that the sample size here is 5 in each case. All right. I want to find the average. This group. Here's my sample average. And I want to find the sample standard deviation, so for that I do STD, standard deviation. Remember, I'm doing a sample one. Oops. And that's the group I want to use. And so this should already the correct ones, G3 through G7, and G3 through G7. Alright, so there's my values, and then N1 and N2 are both 5. So from these 4 values and those 2 values of 5, I can run my test. All right. So let's go to Bogner's calculator. I'm trying to do a hypothesis test for a difference of means. So it's going to look like mu1 minus mu2. I click right here on inference for mu1 minus mu2. You would use a 2-sample t-test if you're using your TI to do this. And there are other calculators that will do this as well, but these are the 2 that I'm most familiar with, and this is the free one. So it's the one I'm going to show you here today. I had 5 in both cases. What was my first sample average? 53.452. And I don't have sigma, I only have S. And I have no reason to assume that their standard deviations are the same. This assumption, when you have good evidence for it, can actually give you a more powerful test. But most of the time you will not have evidence for that. Unless you are told to assume that the 2 standard deviations are the same, select the option that they are not. Now, what was my sample variance? Sample standard deviation, 3.70763. And in my second case, 53.628 was my average. And my standard deviation is 1.9455. All right. In fact, if anything, this seems to indicate that they might not be different, or not be the same, excuse me. Okay. So here's the test I would run. And you'll notice my degrees of freedom is this long, complicated mess. Comes out to just over 6. Now I want to run a hypothesis test. I'm testing whether it's 0, and if it's not, the conclusion I want is that it's not equal to 0. So I'm doing a 2-tailed test because of that. I am using alpha equals 0.05. Remember, not always will we be doing that. Sometimes we use a different value. And if it's not on this list, that's okay. You're just comparing it to p. The only thing that will happen is you won't get the right picture. So when I run this, my test statistic is negative 0.094, and that is not large enough for me to reject the null hypothesis, and I can see that clearly when I look at the p-value. My p-value here is 0.928. What that means is, if it's true that there is no difference, I will see a sample with a difference as large as the difference I observed, which I guess is negative 0.176 seconds. I'll see a sample difference that large or larger about 92.8% of the time, if the null hypothesis is true. Well, that's a lot of the time. That means more often than not, by quite a lot, I will see differences this large or larger. That is not enough evidence to reject the null hypothesis, so we fail to reject. Okay. All right. Questions about that? So there is not enough evidence that the mean time to finish is different for these 2 randomized heats, and that's good because that's the purpose of randomization. We really want the 2 groups to be representative samples. We want them to be equally distributed and equally likely to have the same averages. Okay. All right. Excuse me. So let's try another one. Do customers spend more money when they shop at Target or when they shop at Walmart? Okay. So the researchers asking this question collected a random sample from shoppers at each store, and the summary statistics are given in this table here. So we have a sample of 85 Target shoppers with an average of 40 and a sample standard deviation of 21. Obviously, we're trying to make the numbers nice here, so it's a little easier to work with. And at Walmart, we had 82 shoppers with an average of 50 and a standard deviation, sample standard deviation of 18. So we want to run our hypothesis test to see whether these 2 means come from different populations. That is, do the population means actually have different values? Okay. So what hypotheses would we use? Let's jump over the document cam and let's write it down this way. All right, so for target, N was 85, X bar was 40, and S was 21. And for Walmart, N was 82, X bar was 50, and S was 18. Okay. So what I want to test is when I take the difference between Target and Walmart on average among the entire population, I want to know, is that equal to 0? If it is, then these two averages are the same. So that's my null hypothesis. The alternative, since I'm just asking if they're different, I'm not trying to conclude one direction or the other, my alternative is that they are not equal to. Alright, I need to check the 3 conditions. First, independence within each group. That is, are these 85 target shoppers independent of each other? Well, I'm told that it's a random sample of shoppers at Target that were collected here, so that randomization gives me the independence assumption. That's for Target. And the same thing is true for Walmart. I'm told that we have a randomly collected sample, so that randomization condition gives me the independence within the groups. I'll even emphasize here, within groups. So that's satisfied. My other marker works better here. I also need independence between the groups. That is, I need that this group is independent of this group. Knowing that a particular Target shopper spent $45 does not necessarily help me know what a particular Walmart shopper spent. Right? It stands to reason that those two groups, being separate groups, are going to be independent of each other. Now, if these were the same individuals shopping at Target on one day and Walmart on another day, they might have shopping preferences or shopping habits that would be related. And so I would see a connection between the values at Target and the values at Walmart. But if these are completely separate groups, maybe collected on the same day, presumably they don't include the same individuals, then they would be independent. And so that means independent of groups, between groups, is also satisfied. Now the last thing I need to know here, are they nearly normal? I'm not given any information. So if I were truly running this test, I would want to take the 85 values that I got from Target and the 82 values I got from Walmart and separately create a histogram for each and look at those histograms. Do they seem to look nearly normal? Do they appear to have a unimodal and symmetric distribution? If so, then they are nearly normal. Okay. On the other hand, I have well more than 30 in each group, and so the central limit theorem here tells me that I'd expect the sampling distribution to be nearly normal, and so I think I can conclude that in this case. All right, so once I have those three conditions satisfied, then the distribution I want to use does apply. My degrees of freedom here is not going to be a nice number. It's going to be, let's see, 21 squared over 85 plus 18 squared over 82, quantity squared, as the numerator, over 1 over 84 times 21 squared over 40, quantity squared, plus 1 over 81 times 18 squared over 50, quantity squared. And that'll all be in the denominator. We'll see all of that on Bogner's calculator. I'm not even going to bother to write it down here, that's just too much writing. It's definitely not the right choice to try to do this by hand. Even if the numbers are this nice, it's still going to be a pretty nasty fraction when I do it. Alright, so let's check what happens there. Let's now jump over to Bogner's calculator. And I'll just emphasize again, To do this, I go to inference for mu1 minus mu2. And I had 85 target shoppers and 82 Walmart shoppers. The target shoppers averaged 40. The Walmart shoppers averaged 50. I don't have access to the population values, and I have no reason to assume that the standard deviation among the two groups is the same. So I'm going to use 21, which was the calculated value there, and 18, which is the calculated value there, and then look at the resulting distribution.
Sorry, I had to do this on Bogna's calculator real quick to see for myself, because I've been struggling a little with this class and trying to pass it so I can see fully what it is. I might do some other homework stuff. And I want to show, and it does show me the equation. I can't really move this right now. Let's see if I got the same thing as him. Assume... hold on. I think I'm on the wrong calculator. Statistical inference. How does he get the assume? Okay.
So here's what I was referring to as the formula for the degrees of freedom. And once again, this is not an integer. Right, degrees of freedom here is about 163-ish. If you were to do this by hand, you would want to round down to 162, because that's the maximum integer number that you can actually assume here. But with a calculator, we can take the full degrees of freedom that this computes. We are running a hypothesis test to see if it is 0, and if it is not, we simply want to conclude that it's different from 0, so a two-tailed test. That's the correct level of significance that I want to use. So I'm looking for a critical value a little bit more than 1.97. And the value I get, negative 3.3, is well outside that range. So I definitely have enough evidence here to conclude that these two groups are different. This is the critical value. If I'm at least 1.975 away from the center in either direction, then I have enough evidence to reject the null hypothesis. And it turns out that I'm about 3.3 standard deviations below. It's way over here, so far that you can't even see it in the picture. So this is where my test statistic fell. And because of that, I have enough evidence to reject the null hypothesis. In this case, I do believe that the average amount spent by Target shoppers and the average amount spent by Walmart shoppers is different. Because of the way I ran my tests, all I can conclude is that they are different. I cannot conclude that one is bigger than the other. And this is another place to emphasize, we write these hypotheses before we collect the data, before we run the test. After you run the test, if you do conclude that they're different, you don't get to then jump in and say, oh, not only are they different, but Target shoppers spend less, right, because it's negative. No, that was not the way the test was set up. If you wanted to test that, you needed to run the test with less than as your alternative. Okay? And if we set it up that way originally, then that would be okay. We did not here, so we cannot draw that conclusion. All right, any questions about that example? Okay. When you are running a test comparing two proportions or two means, always make sure you have checked those conditions. In the case of some of the homework questions, it may be the case that you don't have enough information to know for sure. You still should make it a habit to always check those conditions, because if you are doing this independently as part of your job or as part of a later course where you're running some research statistics, you will need to explain why the distribution you used to compute your p-value and decide whether to reject or fail to reject is the appropriate distribution to use. Talking to my father about this, he earned a master's degree in statistics and spent most of his career working as a, well, among other things, a financial analyst. You might call him nowadays a data analyst for Tennessee Valley Authority. What he would do is he would write programs to collect data, mostly financial data, and then use SAS to run a statistical analysis of it, and then he would compose reports to tell his bosses about whatever it was that they were asking questions about. And as part of this process, he consistently had to make decisions about which test can I run and which test can I not run. He had to decide, can I assume that the variances here are equal or are not? Should I pool the variances? Should I not pool the variances? And asking those questions, checking those conditions, was a central part of what he does, because if you don't have the requisite conditions, then you cannot trust the results of the test you are running. And very often what happened was he ended up having to not assume things that he would like to assume that would make the test easy, and he had to run other types of tests that don't have the same stringent list of conditions to check. It is very important to check those conditions before you run any test that you use. One of the values of non-parametric statistics is that they don't make many assumptions at all. And so if you learn some of the more complicated tests in a later statistics course, you'll learn how you can handle situations where you don't have these nice simplifying assumptions available to you. All right. So this is another good place to take a quick break. We really only have one example in the next part, so we might finish a little early today, which would be great. On my clock, it is 10:41. So let's take a 5-minute break and return at 10:46. See you at 5. Any questions about hypothesis tests comparing two means? Just to remind you, there is a situation where you could do a hypothesis test of two means using a standard normal distribution, the standard Z distribution, but it requires you to know both the population standard deviation for group 1 and the population standard deviation for group 2. And that is a rare event. You also would need a large enough sample from each group. And so if either or both of those things are violated, then you have to use a t-distribution. And in that situation, it works very much like the t-distribution we would expect to see, but the degrees of freedom is just kind of a nightmare to work with. So I would strongly encourage you to always use your calculator to compute both the degrees of freedom and to run the test itself. All right. So we did promise that we would also talk about what to happen when you have what to do, when you have paired samples. And so, what kind of a situation might we be looking at if we have a set of paired data? So, for instance, a question you might want to ask yourself: if you are interested in taking the LSAT, maybe you want to go to law school and be a lawyer, then you might want to know, is the prep course I'm looking at here worthwhile? Will it help me raise my LSAT scores and therefore have a better chance of admission and or financial aid at the institution I plan to attend? All right, so that's a question you might want to ask, and what we would want to do is we want to compare what happens to test takers before the prep course and to test takers after the prep course. And it would be ideal to do this with the same individual. Take a pre-test, take a post-test, and see which one they do better on. And if so, by how much. If they don't do any better, then that test prep course is definitely not worth it. However, if they do perform better, then depending upon how much better and how likely it is that that will work out, it might be worth your while to do so, especially if you're dead set on going to law school. You might also ask other interesting questions. Is an older sibling more likely to be better at a computer game than their younger sibling? Maybe, maybe not. But if we're pairing siblings, then maybe this one family plays a lot of computer games and this other family doesn't. For lots of different reasons, we might see a connection between those two groups, and we are pairing one sibling with another. So we're pairing those things up. They're definitely not independent groups. Knowing that an older sibling performs very well at a game might help me know whether the younger sibling performs very well or does not perform well at all. Right, so again, I might see a connection between those two groups. So the independence of groups assumption here is violated. I cannot use that two-sample t-test. But because they involve pair data, what I can do is I can take advantage of that pairing and use the pair of values to produce a single difference. Once I have that, I have a collection of sample values that say single sample, and then I can use everything that I learned in the previous chapter, in Module 8, to know how to test that set of differences. Questions? Sorry, I thought I heard someone. Alright, so this is the idea. We simply compute the difference between each pair, and then we test whether that difference is equal to 0 as a single sample. And that gives us then a one-sample t-test. Right? It will work very much like the ones we had before. The degrees of freedom in this case is one less than the number of pairs that we collected. Right? If they're all paired up, maybe we have 15 total pairs, then the degrees of freedom would be 14, n minus 1, where n is the number of pairs that I'm computing a difference for. So I always like to do at least one example. And so this example would be whether a company's plan to institute an exercise break might improve job satisfaction. So the way they're doing this is they're going to randomly select a collection of 10 workers to respond to a questionnaire both before and after they institute this exercise break policy. And the responses among those 10 workers are included here. This is the score they had, their job satisfaction index score, based on that questionnaire, before and after the survey. And the question is, did the, before and after the exercise break was instituted, excuse me, the question is, did the exercise break actually make a difference? Did it actually improve their workers' satisfaction levels? So in this case, let's assume we're trying to see whether it actually improved it. That will change our alternative hypothesis a little bit. All right, so what I want to do is I want to compare the before and the after. And the way I set this up, if I want to know whether the after was bigger, what I'm going to do is I'm going to take 31 minus 32, 33 minus 26, 48 minus 27, and compare each of those things to 0. Okay. This person apparently dislikes the exercise breaks, but these people seem to like it. These two did. Now, how do I do that? The easiest way to do it is to set it up in your favorite spreadsheet program. Just write out list 1 in one row and list 2 in another. Let's see if I can make this a little bigger. There we go. So I copied and pasted this over. Unfortunately, I had to do the formatting thing to list them in separate columns, but it's not too hard to do that with whole numbers like this. And so what I'm computing now is the differences after minus before. That's what I'm going to compute. So the after minus the before. That will tell me the net change for that individual after they have instituted the exercise program. I click and drag to compute this for all 10 values. I now see the net change for each individual. These two people were unhappy, or less happy, I guess I would say, after the exercise program, but the others seem to all have higher scores. So this is looking promising. What I will want to do, copy that, is to run a one-sample t-test for this group. Okay, now I have 10 values, so I will have 9 degrees of freedom. I'm going to jump over to Bognar's calculator for one sample, so inference from U here, and I'll be entering raw data. Now before I do everything with this, I'll need to add in commas so that it can recognize those different values. But before I do that, I need to check the conditions necessary for this one sample t-test. So the first condition, I need to check the independence assumption. When I look at the 10 differences that I'm using to run this test here, are those 10 differences independent of each other? If they collected a random sample of 10 workers, that randomization should give me that one worker's difference does not influence the other. Right? If they happen to work with desks right next to each other, maybe one of them complains constantly about the exercise program, that might change the person's evaluation of the exercise program. But if I do a random selection of 10 workers, then that should be sufficient. I also need to check the nearly normal condition. And here I don't have enough information to know for sure. For the sake of argument, let's assume that the distribution of the scores in this questionnaire in both cases are nearly normal, and in that case, using the expected value and the variance calculations I found before, the differences will also be nearly normal. So if I did the histogram, for instance, I could see that it would be unimodal and symmetrical. Okay. So if I have the conditions necessary, I can run my test. Let me make it clear that these are all
Are you coming down to get some satisfaction from that?
different values.
I was like hoping, but you're doing stuff so.
Alright. And thankfully, Bogdan's calculator does all the calculations here for me. There are 10 values included in my set. The average, 0.8, that means on average among these 10 workers, their job satisfaction index went up by 9.8 points. And the sample standard deviation among this group of 10 workers was about 7.5, a little bit less than that. Now I want to test whether they had exactly the same, or whether it improved. Actually, wait. After minus before, yes. The after minus before should be bigger than 0 if I'm going to conclude that it actually improved their job satisfaction. So I do need my alternative to be greater than here. Always ask yourself, what would it mean for this difference to be bigger than 0? And the way I framed it, after minus before is bigger than 0 if after is bigger than before. So if they were happier after than they were before. That's what I need to know if I'm going to decide that this program is effective. Alright, so we run our test. We have 9 degrees of freedom. We want to run it with maybe a 5% significance level. So here's what my one-tailed test looks like now, since I want to conclude only in one direction. Hopefully this exercise program doesn't hurt their job satisfaction. Right, I'd like to conclude that it actually helps. That's a one-tailed test. I get a test statistic of 4.168. That's pretty promising. That's a large test score. And that corresponds to a p-value of 0.00121. That is a very small p-value. That means this sample would be exceptionally unlikely if it's true that the exercise program had no impact. If it's true that the job satisfaction was the same both before as it was after, then this sample would be just more than 1 in 1,000. Right, I guess it's 1 in 800 roughly. Right. That's pretty unusual. So if it's a 1 in 800 sample, that's enough for me to say I don't believe that they are the same. I don't believe that there was no impact to this exercise program, so I think it actually did improve the job satisfaction, and it's worthwhile to institute it as a permanent policy. I reject the null hypothesis and conclude instead that there is a difference between the two groups. Okay. All right, so the key thing in paired tests is first recognizing that you have a paired sample. The most common situation is a before and an after with a treatment of something in particular. In this case, the treatment is the exercise program. It could also be, if we're doing an experimental drug, if I'm looking at what happens before they take the drug versus after. That's a paired sample. Okay. On the other hand, what I could do is I could have two separate groups. One group gets a placebo, and one group gets the actual drug. That's two samples. If it's not the same individuals who are being involved, or if there's not a connection between individual one and a specific individual in the other group. Okay. If they are the same individuals, however, then they are paired, and I want to use that as a one sample test where I literally compute the difference within the pair. Okay. All right. Any questions then about any portion of what we discussed today? All right. In that case, I will give you back some time in your day. I will fix the Module 9 deadline when I get... Get it back to my office, so it should be good by before noon at the latest. And at that point, you will have until next Wednesday to complete the Module 9 homework. As always, if you have any questions about it, please feel free to email me. I'm happy to answer those by email during my office hours Tuesday and Wednesday next week, in a separate Zoom meeting if you can't make those hours, or at